Okay, so thank you, Roman, for your kind introduction, and good afternoon, ladies and gentlemen. The title of the following talk, prepared by Michael Haring and myself, is a Gibbs Ensemble Monte Carlo simulation software suite implemented in Wolfram. So today we report on a Monte Carlo simulation program that was implemented entirely in Wolfram language and compared to conventional program packages, therefore offers much more diverse evaluation options like tracking of convergence behavior, output of intermediate results, and so on, in addition to simple expandability. So to give you a short outline of my talk, I will start with the motivation for implementing a Monte Carlo program in the Wolfram language. Then I will give a brief outline of the project in terms of the key features of the software and its typical application in my group. After that, I will present the implementation of the software to show its structure and the basic ideas applied to code design. And afterwards, I will show what we consider as the benefits of using Wolfram in contrast to conventional implementations. And finally, I will summarize my talk and give a brief outlook of the intended next steps for further development. So to start with the motivation for this project, I would like to shortly explain the basic idea of Monte Carlo for those who are not quite familiar with this approach. So-called Monte Carlo experiments are a class of algorithms that are used that use repeated random sampling to gain some numerical results. So they rely on random experiments to solve problems that are actually deterministic in nature. And these methods are applied for things like numerical integration, optimization, or sampling from a probability distribution. So historically, such computer simulations started as a tool to exploit the first electronic computers that had been developed during and after the Second World War, which had been designed to perform very heavy computations involved in the development of nuclear weapons or code breaking. And after that, the first simulation of a liquid was carried out in 1952 by Nicolas Metropolis on the ENIAC computer at Los Alamos. And this was the starting point for applications in chemical engineering and statistical physics in the field of molecular simulations. Now, in our case, we apply Monte Carlo to a so-called Gibbs ensemble to conduct molecular simulations of phase equilibria, which means we set up two boxes, one for the vapor phase, one for the liquid phase, to simulate the boiling of a liquid in coexistence with the vapor. And for that purpose, the boxes, as you see, are initially filled with molecules and then undergo so-called Monte Carlo moves, which are illustrated in the figure below. So starting from the initial configurations of the particles in the boxes, a molecule is picked out randomly and then either moved within its own box in terms of a translation, or it is picked out of its own box and transferred to another box, here transfer, or the box volumes are changed. And in a quite similar way, additional Monte Carlo moves can be applied to more complex multi-atom molecules, like the rotation of a molecule or its constituents, as well as bond stretching or angle bending can also be considered. And these Monte Carlo moves are then repeatedly conducted in order to shift the system towards a minimum of its internal energy, which finally brings the system to the vapor-liquid equilibrium. And typically, these moves are organized in such a way that first of all, there's a so-called warm-up phase for moving the system away from its initial configuration. After that, there's an equilibration phase for bringing the system to equilibrium. And finally, there's a production phase during which the averages are calculated to gain the mean bulk properties of the system. And the purpose of such an organization is simply to apply different strategies for trial moves during each phase separately to achieve equilibrium more quickly overall. And the typical application of such a simulation is the determination of fluid phase properties like saturation pressure or saturation densities for a given temperature, whereby such simulations are to be seen supplementary to experiments. For example, for substances that are difficult to obtain or expansive in pure form, or for states which are at extremely high pressures or temperatures. Now, why choose the Wolfram language for such a simulation? Well, actually, the structure of these Monte Carlo algorithms, which basically consist of some nested loops, which suggest the use of Fortran or C, where these languages can play to their strength. And indeed, most open source software packages for Gibbs Ensemble Monte Carlo simulations are actually implemented as quite monolithic Fortran or C code. But these codes often only communicate with the user in a rudimentary way using text files. And as a consequence, the users are reluctant to change or extend such programs because it takes longer to familiarize themselves with the code than if they were to rewrite the program from scratch by themselves. And for these reasons, it was attractive for us to fully implement a Gibbs Ensemble Monte Carlo simulation in the Wolfram language ecosystem, mainly addressing three goals. In particular, firstly, to provide a fairly intuitive user communication. So we have one and the same language for calculation, evaluation, and make use of the Wolfram packages. We further use simple switch statements in the user interface, and is illustrated here. And in non-time critical situations, we make use of the symbolic derivatives instead of hard-coded equations. For example, if you would like to derive an equation of state from a fundamental equation, or you want to calculate the fugacity coefficient from an equation of state, then these symbolic derivatives and integrations are very, very nice to have. Okay, the second point is to ensure a simple expandability of the program. We use basically a global variable environment in non-compiled functions. Then the use of packages provides an easy collection of data and of parameters, and we use templates for code extensions. And the third motivation was that we can use the diverse visualization options of the Wolfram language, as I will show later in this talk. So to give you a short outline of the project, I would like to begin with some key features of the program. So we use the so-called optimized potential for liquid simulations force field in its all-atom variant, OPLS-AE, which is proposed by William Jorgensen and considers every atom of a molecule explicitly. For mixtures, we have various mixing and combining rules available, like geometric mean or the rules of the Lorentz-Berthelot type. The program provides an improved insertion algorithm for binary mixtures to increase the acceptance rate of molecule transfers based on identity changes, as proposed by Professor Paniatopoulos. Then we implemented the so-called continuous fractional component, or CFC method, which was developed in the working group by Thijs Vlucht, and it improves the insertion probabilities into the liquid at high densities. Then we use an auto-calibration for the number of attempted transfers per cycle to yield the required number of successful trial moves per cycle. Furthermore, the probability to choose a species for an attempted insertion can be tuned or auto-calibrated to yield an equal number of successful transfers for each species. Next, the radial distribution function is determined either using a histogram-based method or a force field-based method, and also the cavity correlation function is sampled. These are very important and frequently used functions in the context of integral equation theories. Last but not least, the software permits a combined analysis of results of multiple continuous simulations, which is in particular helpful in an environment with multiple and distributed simulators, I will come back to this feature a little bit later. So to talk about the application of the software, this simulation suite is being used in both research and teaching. For example, we published a kind of pedagogic summary of the continuous fractional component method, which was developed in the working group of Thijs Vlucht and ensures an improved transfer rate into the liquid box at high densities. And here we provided several application examples using our software suite. In the second paper, we implemented an auto-calibration strategy for the equilibration phase in order to enter the production phase with an optimized set of trial moves. And currently, we use the software to determine the radial distribution functions from simulations as exact as possible, to gain information about the local density of a fluid as a function of distance from a central molecule. So here you see the principle, a central molecule, and the local density in a certain distance is given by these radial distribution functions. Here you see a typical curvature. Okay, and finally, it should be mentioned that all applications up to now focused on relatively small molecules, so there's no intention at the moment to implement features that optimize the simulation of very large molecules. By the way, yeah, we use it in teaching also. So the program represents the core of a lecture about model development and simulation, which is also a great opportunity for the developers to receive kind of feedback from students using the simulation suite, which is of course important to further improve the user friendliness of the software. And beginning with next winter semester, we will also use it in the lecture Fluid Phase Properties to demonstrate the estimation of physical property data using molecular simulation. By the way, the software package is available on the notebook archive hosted by the Wolfram Foundation, where we also provide updates on a regular basis. Next, a word on the implementation structure, which was derived from a typical simulation workflow. And accordingly, the simulation suite consists of approximately 6 separate files. So there's one notebook for the estimation of starting values for densities and pressures, for example, using equations of state or activity coefficient models. And then we have 5 separate Wolfram Language script files. So one is for the simulation setup. Then one is for the execution on a workstation or an execution handler for execution on a computer cluster where you have several nodes. Because in particular, we also run the software on the Vienna Scientific Cluster, which represents an Austrian initiative of high-performance computing. Then there's one notebook for the analysis, either of single simulations and a combined analysis of multiple simulations. And last but not least, there's one notebook for extension of a simulation, which, for example, did not quite reach the equilibrium or had an insufficient number of production cycles, so that averaging was not satisfying. And all this script I mentioned rely on a number of packages you see on the right-hand side here, which provide things like thermodynamic models, for example, equations of state, flash calculations, phase diagrams, which are especially useful for the estimation of start values. And furthermore, these packages provide force field parameters, physical property data compiled from different data banks like NIST or the Dortmund data bank. Okay, since these Monte Carlo simulations repeat the Monte Carlo steps many times, it's important to optimize the individual Monte Carlo moves in terms of calculation time, which I would like to illustrate here by an example. So concerning the data type, it makes a huge difference whether you use just lists of reals or if you use advanced data types that use an internally more efficient storage format like the packed arrays. Second, it's very important to choose an appropriate data structure. So for example, the list of intermolecular energies is a symmetric matrix. And consequently, instead of using a matrix as a list of lists, it's more efficient to use only the upper triangular matrix, again in terms of a packed array. Then third, for the energy calculations, we started in the beginning with multiple redundant functions depending on whether they were applied to single values or lists, and then switched to one single listable function that is automatically threaded over a list in case the argument is a list instead of a single value. Another thing is, of course, to avoid any unnecessary calculation. For example, to calculate the distance of 2 points in three-dimensional space, you can, of course, use the intrinsic norm symbol of the Wolfram language. But if you only need the squared radial distance, it saves a lot of time to calculate this directly and avoid the square roots, which is computationally expensive. Next, it can be more efficient to avoid using vectors or lists in compiled operations and to replace them by single arguments instead. Probably this avoids time-consuming checking of the arguments by the compiler. And last but not least, it's important to check the software from time to time in view of avoidable calculations that are not necessary for each trial move, but only once per cycle, for example. So to summarize, code optimization should not be an afterthought. And in this particular example of one of the trial moves, the calculation time could be reduced by a factor of 18 just by taking the measures I just presented here. However, it should be mentioned that even more extensive optimizations would require certainly deeper insights into how the compiler works, which is of course beyond the scope of ordinary programmers like us. Okay, to talk about code design, we use Wolfram Language scripts instead of notebooks, because these can be used both on a personal computer and a computer cluster. And they are also somewhat more resource-friendly when it comes to using GitLab for code management. At the moment, the code itself is a mix of compiled functions with delayed functions in order to speed up evaluation while using non-compilable data types, where we use either the Wolfram virtual machine or an external C compiler. And last but not least, we use the listable attributes just to facilitate the handling of non-tensor objects, as well as allowing the function to run in parallel. Last but not least, what is important in a distributed computing environment is the management of multiple simulators, for example, in the form of multiple virtual machines that are available. And for such a situation, the software is prepared to be operated from a local computer that makes the simulation setup files available to a number of remote computers via the GitLab server, from which the remote pulls these setups, executes the simulations, and then pushes back the results to the Git server, from which they can be pulled by the local computer for a combined analysis of the results. Okay, now having explained the implementation of this Gibbs Ensemble Monte Carlo suite, I would like to outline what we consider to be a benefit of using the Wolfram language compared to a conventional implementation, for example, in Fortran. And this benefit can be best summarized in one sentence: a picture is worth 1,000 words, which of course refers to the diverse visualization options of the Wolfram language that makes a difference, and of which I would like to give you just a few examples. So beginning with the estimation of start values for the simulations. So these can be predicted using equations of state or activity coefficient models and can be visualized together with experiment data if these are available. So this is illustrated on the left-hand side by a density temperature diagram with the bubble line, the dew line, and the critical point, indicating the proposed starting values for the coexisting densities. On the right-hand side, the vapor and liquid molar fractions of a binary mixture are proposed, illustrated in a vapor pressure diagram, again using an equation of state, here the Schwarzschild-Friedrich-Kwong equation. So this can be used as starting values and input for the simulation setup. So with these starting values, in next step, the simulation can be set up where the molecules are chosen from a mole file and can be visualized as shown here. Then they are parameterized for the selected force field, including a check whether all necessary parameters could be supplied and were available. Then the filling of the two boxes is visualized and can be checked for plausibility, as shown here on the right-hand side. Then, having completed all the required inputs, a final check is provided before the setup is exported and executed as a next step. And this check includes the state variables, the particle numbers in the boxes, the simulation details, like the number of warm-up cycles, equilibration cycles, and production cycles, and the proposed trial numbers per cycle. So during the execution of the simulation, the convergence behavior can be tracked for warm-up, equilibration, and production phase, and indicate a rough estimation of the remaining time. And this dynamic tracking is intended to look in from time to time and check whether density and particle numbers in the boxes are converging, as you see here, or if there are issues like oscillations or frequent phase changes in the boxes that would suggest to abort the simulation and rerun it after adjusting some parameters. Of course, such a dynamic tracking naturally costs computation time, but this can be prevented by just simply minimizing the notebook window and only using the dynamic tracking from time to time. So once the actual simulation has been completed, the results are analyzed by executing the analysis script. And as a first analysis tool, a so-called Frankel plot is used. Here the fraction of the total volume taken up by a box is plotted versus the fraction of all particles in the box. Every dot represents a point sampled in the simulation. And now the closer these points cluster around the 2 points that correspond to the coexisting liquid and vapor state, the better the convergence. So the smallness of the two surfaces here is a kind of measure of a good convergence. This convergence can, of course, also be assessed by tracking the evolution of bulk quantities of the system. In this example here, we see the evolution of molecule numbers, particle numbers, number densities during the equilibration phase, which is light gray shaded, and the production phase, which is dark gray shaded. Next, the acceptance rates of the trial moves are another very important quantity that give you a feedback on the effectiveness of the trial moves. This example here shows the acceptance rates of bond stretches and angle bands, where we see roughly the same number of accepted and rejected trial moves, which indicates a fairly sound distribution of these moves. What is also important are plausibility checks regarding the final particle numbers in the respective boxes, as well as the accepted insertions over the equilibration and production period. And finally, the radial distribution function for each atom species can be checked visually, giving an impression about the structure of the vapor and liquid box in terms of the local density at some distance from a reference atom. Last but not least, the extension of a simulation is possible. This is for the case that a satisfactory convergence has not been achieved, either because the simulation simply did not equilibrate or had an insufficient number of production cycles. So using the last of these script files, is it possible to specify additional equilibration or production cycles, as well as adjustments of the trial move limits. And this option of an extension is a great means to avoid wasting simulation time by simply recycling an existing and unsatisfactorily converged simulation and converge them. And furthermore, if you work on a computer cluster, you often get a limited maximum job time, for example, 3 days. So also in this case, the extension tool is a valuable thing to conduct long simulations that exceed this maximum job time. Now to summarize my talk, we implemented a Monte Carlo simulation program entirely in the Wolfram language, and the resulting simulation package offers a wide range of visualization and evaluation options compared to existing packages that only communicate with the user using text files. And from our experience hitherto, this lowers the inhibition threshold for using such a program and also contributes to a more efficient and effective workflow even for experienced simulators. And as an outlook, we think of transferring the simulation to a package structure with support from Wolfram. And a further step could also be to change over to function compile and its consistent use. Of course, once it is clear how to get over the related loss of the listable attribute and handling of non-tensor objects. So, and with this outlook, I would like to thank the entire development team listed here for their great commitment to this project over the last 5 years. And I would like to thank you for your kind attention. Thank you very much.